We all hear about the speed of light. We know it's fast, like ridiculously fast, but we usually just think of it as a number, right? The universe's ultimate speed limit. But it is so much more than that. It's not some arbitrary rule. It's a fundamental property that's literally woven into the fabric of reality itself.
So let's get right into it. We're always told nothing can go faster than light. But why? I mean, really, have you ever stopped to think about what's actually stopping you? What's the barrier? Is it some kind of cosmic police officer? What physically prevents you from just pushing the throttle a little bit harder and breaking through? Well, the answer is stranger and frankly a lot cooler than you might think.
And there it is, the number. Almost 300 million meters every single second. It's a figure so huge, it's almost impossible to wrap your head around. But here's the thing. The number itself isn't the important part. What really matters is what that number represents.
And this is the key takeaway right from the start. The speed of light isn't a limit that's imposed on the universe. It's a direct consequence of the universe. It's a built-in feature of space-time. And to really get it, we have to follow a trail of clues, a sort of detective story left behind by some of the greatest minds in history.
Yeah, we didn't just figure this out overnight. It was more like an avalanche of discovery, a chain reaction, where each new insight made the next one possible. It all built on itself, leading us down this incredible path. And it all kicked off more than 300 years ago, with a surprisingly simple thought about the moon.
So here's a quick look at how this all connects. It really starts with Newton, who gives us the rules for gravity. Then, because Newton's work was so solid, an astronomer named Ole Romer felt confident enough to make a really bold claim about the speed of light. And that discovery, centuries later, set the stage for Einstein to come along and completely flip our understanding of space and time on its head.
You see, Newton's big aha moment was realizing that the moon wasn't just some magical object floating up there. It was actually falling towards the Earth all the time. So why doesn't it crash? Because it's also moving sideways so incredibly fast that it keeps missing us. An orbit, really, is just the art of falling and missing forever.
Now, the way Newton proved this was just genius. He figured out that gravity follows what's called an inverse square law. Basically, the farther away you get, the weaker the pull, and it weakens by the square of the distance. He calculated that since the moon is 60 times farther from Earth's center than we are, gravity up there should be 3,600 times weaker. And when he ran the numbers, the rate the moon falls was a perfect match. His law worked. It was unbelievably accurate.
And this is where that avalanche really gets going, because Newton's law was such a powerful and trusted tool. When later astronomers saw something in the sky that didn't seem to follow the rules, their first thought wasn't, oh, Newton must be wrong. Instead, they said, okay, something else must be going on here.
And that something else was popping up in the orbits of Jupiter's moons. According to Newton, those moons should have been moving like perfect clockwork. But that's not what people observed. They saw that sometimes the moons were a full 8 minutes ahead of schedule, and other times they were 8 minutes behind. And the weirdest part? It all depended on whether Earth and Jupiter were on the same side of the sun or on opposite sides.
Now this, right here, is just beautiful science in action. The astronomer Ole Romer, having complete faith in Newton's law, made this incredible leap. He said, "The law isn't wrong. Our assumption is wrong. We've been assuming we see things the instant they happen." Romer realized that the 16-minute difference he was seeing was simply the time it took for light to cross the vast distance of Earth's orbit. And just like that, for the very first time in history, someone had proved that light has a finite speed.
Okay, so now we know light has a speed. Great. But as our measurements got better and better, a much deeper, much weirder puzzle started to emerge. And this was a puzzle so strange that it would take someone like Albert Einstein to even begin to unravel it.
Just think about this for a second. If you're on a train moving at, say, 50 miles per hour, and you throw a baseball forward at 50 miles per hour, someone on the ground sees that ball moving at 100, right? Speeds just add up. It makes perfect sense. But light just doesn't care about our common sense. If you're on a spaceship moving at 99% the speed of light and you turn on a flashlight, that light beam doesn't move at 199% light speed. Nope. It moves at exactly the speed of light, every single time.
And this is the completely bonkers, impossible puzzle that Einstein had to solve. The speed of light is constant. It does not matter if you're racing toward the light source or running away from it. It doesn't matter how fast you're going. You will always measure its speed to be exactly the same. This idea just shatters our everyday intuition.
So how is that even possible? Well, Einstein's solution was absolutely revolutionary. He realized that for the speed of light to stay the same for everyone, something else we thought was constant has to give. And that something else is space and time itself. He proposed that they aren't this fixed, rigid backdrop to the universe. They're a dynamic, flexible fabric that can actually stretch and shrink.
And this radical idea leads to two totally wild consequences. First is time dilation. The faster you move through space, the slower you move through time. Your watch literally ticks slower than the watch of someone standing still. And second, there's length contraction. The space in front of a fast-moving object actually gets compressed in the direction it's moving. The universe itself physically warps just to make sure that the speed of light is always the same for everybody.
So that brings us to the final piece of this puzzle. Why? Why does the universe go to all this trouble? The ultimate answer doesn't lie in rules or limits, but in the actual, fundamental geometry of reality itself.
And this is where it all comes together in this really beautiful way. Einstein showed us that we should stop thinking about space and time as two separate things. They're actually two parts of one single unified entity, a four-dimensional fabric he called space-time. And everything, you, me, the planets, the stars, everything is moving through it. Okay, now this next idea is maybe the most important one to grasp. You, me, this planet, everything in the universe is constantly moving through space-time at one and only one speed, the speed of light. Right now, as you're sitting there perfectly still, you aren't actually still at all. You are hurtling through the dimension of time at the maximum possible rate. Think of it like this. You have a fixed budget of motion through space-time. You can spend that budget either on moving through space or moving through time. When you're standing still, you spend 100% of your budget traveling through time. But the moment you start to move through space, even just walking across the room, you have to divert some of that motion away from the time dimension and into the space dimension. And that's it. That is why time slows down for you.
And that right there, that's the answer to our question. If you could accelerate until you were using 100% of your motion budget just to travel through space, well, you'd be moving at the speed of light. But at that exact point, you would have zero motion left to spend on traveling through time. For you, time would come to a complete stop. You can't go faster than light because you can't move through time at less than zero. You've hit the floor. There's no more time speed to give. And, this isn't just some wacky theory. We rely on this stuff every single day. The GPS in your phone only works because we constantly adjust the clocks on the satellites, which literally tick at a different rate than ours on the ground. We see tiny short-lived particles called muons created high in the atmosphere that somehow survive long enough to reach the ground, something that would be totally impossible if time didn't slow down for them. This stuff is real.
So let's just bring it all home. The speed of light isn't a barrier you can break through. It's more like a fundamental conversion rate that's built right into the geometry of spacetime. It's the exchange rate between space and time. It's not a limit on reality. In a very real sense, it is reality.
Which leaves us with one last, truly mind-bending thought to chew on. For a photon of light, a particle that travels at light speed, its entire journey, whether it's across a room or across billions of light years of empty space, takes no time at all. From its creation in a distant star to the moment it hits your eye, it all happens in one single frozen instant. So what does the universe even look like from a perspective where time doesn't exist? That's something to think about.